Hello, everyone. Thank you. There was a problem in the morning, so I'm just re-recording. Just want to update. I and Laszlo were talking through WhatsApp today, and Gerd also joined in our text steering committee WhatsApp link video calling. Uh, so essentially, Christian is on Easter vacation, but he will come back and complete our t-shirt design. Then Laszlo will proceed with that, and then he thinks that we can sell for about $22 to $24, but give and take a few dollars. So we will, I think, finalize everything by next weekend. And we are talking about earthquake prediction, and he's preparing for the planet erosion. Uh, you know, Presentation for the conference. And as we know that, let me again briefly mention about our plans. That's almost there. So we have this plan. Uh, so it starts with Christian Wolf, iSpace. Then we have Gerd Pomeranke, Gerd on electron mass to Hubble tension. Then last law we'll talk about, or what we'll talk about, planetary erosion, superluminary condensates, and all that, hot PDP mechanics, etc. I will be talking about. Then Christopher will talk about anamorphic perspective morphology. Uh, and then we have, in between, we have coffee breaks, and I and Christopher will be switching the chair session of the sessions. Then Emmanuel and Markulikis and Antonius Valamentas, they will talk about superluminary graviton vacuum. Again, they have some time, 1 hour. Then we have panel discussion that I will be chairing, and all our members, Christian Wool, Gerd Pomeranke, Christopher O'Neill, will be conducting that, and then Laszlo will also coordinate all the other activities. So I think we have everything set. Then we have closing ceremony, which is all set that night. Even Christopher has, I think, a booked hotel. Seems to be like Indian restaurant, but we have to get details from him. He's busy with his PhD uh, dissertation writing. Now, then the 31st, we'll be all going sightseeing with the hop in, hop off. Then I leave that evening. The Sunday post conference, I will be away. I'll be in Brussels, and hopefully see the Atomium place like that through hop in, hop off. Then the following day, I'll be in Geneva, going to CERN, hopefully see, let's see some part of it. I don't know how much you can see, but I like to visit that place and see what we can come up with, because it is the center, like a temple of physics. So yeah, so that is the main agenda here. And then we let me briefly mention that I have the presentation slides almost ready. Uh, yeah, so I start from here about superluminary condensate, then abstract. But what I want to talk to people about is that I have this slide which may have a lot of information in them, the abstract, for example. But I have another slide that highlights of that. So probably there's two ways I can do it. Either I can use these highlights only, so it will be about 20 slides, or show this one and then say that Yeah, I'll highlight the main points. So these are the main points, the abstract, uh, you know, and then we move on from there. So, so like that, each slide has all the material, but the highlights essentially will, you know, give the main points here. So that's how I set up the slide. Oh, okay, okay,
He'll see
yeah.
you tomorrow.
Huh?
He said he will see us tomorrow. He
Okay,
has to go to bed.
okay. I see. Thanks. All right. So, okay. So action. This is a important slide also. Again, that that you can be like that only. The statics is determined by the equivalence principle, dynamics by the Lagrangian energy aspects. That a lot of it I'll bring out in this presentation. So again, we have that, uh, you know, the whole substance, but then I have the highlights, which brings out only the key points, easier to read and describe, and also to explain, so people can see better. Even we will hopefully have a big screen also, so this will be more easier to read, things like that. I don't want too many so that's one of the reasons I have these two different slides. But also I want to show that I have this much material on them. So if they want to go into detail later on, either during Q&A or especially the panel discussion, they can, or even later after the conference, we still have texts and other discussions that will come up. So this is just a starting point. That's the important point I want to emphasize. Is just it's an initiation point, but we will expand further, uh, more on that. So this is another slide, just graphics here. Again, you can see this one, foundations talks about, and yeah, again the foundations. So again, it's not too much material here, so I think I can leave it there where it is. Uh, and then the outer products, important math here, the matrix math, and then the hot PDP mechanism and the highlights again shows the important points here. Same with the PDP circuit, and it's highlighted slightly different because it's easier to read for only this caption. So I reduced some material so that we can pull out the captions easily. Uh, so it's just a matter of readability and things like that. So again, this is a fairly easy slide, so we'll leave the way it is. And this has lot of material because it describes the whole equation. It's a general transform. Like organic field theory, it's a big equation. It's a whole set. But then I reduce that to this just to show the enormity of the equation we need for general transformation, and then just describe what that is, and I will describe in audio what that is. So like that we can do that. And again, this has small letters and things like that, so I expanded this so we can read it more, and then again emphasizes the picture, which is the instrumentation to measure the light and sound, point the point to point. That specific aspects of this comes out from a purely abstract theory, actually, surprisingly, to the experimental level. And that's the key point in this one. The time quantization, again, it's fairly simple. I mean, readable, and then mainly time quantization. Spin spectroscopy, that's a new one, energy temperature equivalence. And this is the tensor. I think I have the highlight in the next slide. Yeah, it's a highlight, mainly brings out the tensor aspects of the time. So time is both scalar as well as tensor. How that becomes is the main one of the key aspects here. So describe this tensor in terms of this Euler type of uh, angles or rotational angles. So essentially, it's like a rotation matrix, very similar to rotation matrix. So that's the main thing about the time. It's a rotation that goes around, as we know. The eigenvalues are essentially that. And this shows the whole schematics of how the supernumerator becomes create a real matter space. So that's very interesting schematics and your transformation between Euclidean and Riemann. Uh, it's very important because the space, as Christopher will talk about later about the 4D hyperspace, he may touch upon that, some of it. And the Emmanuel will touch upon the superluminal aspects, how the vacuum aspects is. So all of us have a piece of puzzle which are all interlinked, and it all comes to some kind of a graviton, quantum gravity type of thing. Uh, but this is an initiation, so we are only showing our piece of puzzle, but then we have to eventually assemble them. And this is the spin spectroscopy I'm talking about. So using this, which is charge ratio, is a classical thing, very simple. And the spin number, which is comes from the quantum mechanics. So we are trying to make an ensemble where we can actually measure this. We can measure actually LHC. If I have a chance, I will talk with the people when I meet there. And the graviton is somewhere here. So if we can measure these and show these are this, then we can uh, probably get the inference that there should be a graviton here. So that's the idea, and it's very similar to Higgs boson. We can find it will be very similar to Higgs boson. That's my prediction. The graviton will be here, but you cannot measure the graviton, unfortunately, unlike the Higgs boson. Uh, we can only theoretize them, but theoretically infer that. So that's a very important point. And this is a signal. It's a lot of material here. Again, I have highlighted here in this slide the main aspects. The main thing is you can convert all of the signal to noise into a temperature variation, and that's the idea. So we get the two endpoints of the universe. One is superconductivity, the other is vacuum. So that's a very important result of that. And then what we measure are the power spectral density, and you know, uh, and then we can do the manipulation that I talked about with the algorithm to pull out important aspects that I talked about the previous slide as well. So this is, you can interpret them, and then we get the membrane. How we can get the membrane uh, separated by discontinuum and things like that. We can infer from this. Normally from graphs we infer things like that. That's how we, all we get is graphs like that. Even in, let's say, I'm sure we get graphs like that, but we have to interpret them. That's why you need proper theory and a model uh, to interpret them correctly. So again, this is the other aspect of scalar equations, how the Lagrange is connected and things like that. So the math has to connect that, and then 4D or hyperspace that very similar to what Christopher has come up with. But we have, this is my side of it, the time, and his side of it. We have to find a match. We have to put our puzzle pieces together somehow. So this is the whole thing where you scalarize time and gravity, how they come together by scalarizing process. So this is more highlights, which only brings important things that you can actually convert this time tensor into vectors, time vectors, and then combine with the gravity, which is a gradient. When you combine them, you get something like very similar to Schwarzschild matrix type of thing. So quantum gravity aspects. So you have this 4x4 matrix, which is which gives how the interaction of the gravity and time, how the gravity comes into picture. So it's a very interesting thing that we can proceed further with that. So the wave function, gravitational field wave function, and the time wave function, how they interact. One is a bra vector, one is a ket vector. So that's how they come up together. So this is essentially a Lagrange with the scalarized gravity, and then using that we can come up with a general equation of it's a function of this. And actually, I do solve a problem. We can actually solve for the conditions of the classical physics. So this is a solution. Again, like anything else, a lot of uh, uh, you know information here, but I highlighted important things. Uh, so it's a problem-solving thing. So I simplified by using what the Lagrange for classical situation we know is p square over 2m minus the that's the kinetic energy minus the potential energy. And for classical things where you know your mass is not changing, uh, so all these conditions when we use them, we can show that this equivalence principle. This is the important principle for statics, as I mentioned earlier. The earliest, one of the early slides, I mentioned this. Here I mentioned the statics is equivalent. This is the equivalence principle I'm talking about. And this dynamic Lagrangian is the one that was shown a little earlier, as you see, uh, like here. Yeah, the Lagrangian I showed here. This is a Lagrangian that comes here for the so we can equate that. So Lagrangian, which is the kinetic energy, and the potential energy is a static aspect. So we equate that. In this case, that comes to mgh, the potential energy, as we know. So when you put all these, we get the equivalence principle, the direction of the gravitational field. That is the static aspect of scalar classical physics. Okay, we can use this to solve certain important paradoxes and things like that. One of the things I talked about, and we'll pick up on that later on, but simple harmonic in the sense that you hang uh, a ball from a string and keep it in vacuums kind of situation where the environment is not affecting it. We'll see after a long period of time the period my prediction, because of when you apply this equivalence principle, you can show that after a period of time and you have solved this equation with the other equation, the previous equation I'm talking about here, this equation. So this is a dynamic situation of the Lagrangian with the static with the equivalence principle. So the static becomes dynamic. That's what I'm talking about. So how the and you can solve the time aspect of it, and the time then it'll say after a period of time the pendulum start oscillating, which is surprising, which none of the present theories can explain why that should be. But my thing is projection prediction from this is that it will start oscillating. So if you can prove that after a period of, then all my theories are proved right. So that's our idea. The other aspect is analyzing the Dom paradox. Again, that's another thing from Newtonian things that actually uh, for in a way questions about the Newtonian aspect, the Dom paradox, and we can explain it. The first level explanation is that the A equal to minus G, like I said, is a static condition. So it keeps a static condition, but uh, but the dynamics start operating on it, which time. So which means that because of the field there's a multi-directional aspects of the field, like that brought about. Remember the gravitational field I talked about earlier here, the gravity, uh, scalarized gravity, uh, much earlier. Yeah, I think I talked about that much earlier. Yeah, scalarizing gravity. Yeah, the scalar gravity aspects. Yeah. So yeah, so scalarizing the gravity aspect, and then you know, which I showed it here, much easier to read here. The gravitation, the wave function of the gravity, so acts on that, right? So the wave function of the gravity takes a while for it to act. So that's the idea of the Dom paradox. So initially, the static, you are statically, you can balance them, but dynamically there is wave function acting along, okay, in time. So the time and the scalar and the gravity scalarizing, right? It takes time scalarize to interact between the ket of the time wave function and the I'm sorry, the bra of the time wave function and the ket of the gravitational gradient wave function. They take a little bit time to act, and that time is the time that the key thing to the dome paradox. So you can keep the ball on the dome statically balanced for few seconds, and then it start rolling down, and that's what mesmerizing. That's what surprising, that you cannot explain from Newtonian or classical mechanics why it's happening. So it's a combination, like I mentioned, of the classical and the quantum aspect, and this is brought about in the in this one also. In this slide, you can see we need charge, classical uh, parameter, and also a quantum parameter to describe the whole thing. So it's a mix, it's a hybrid of that, uh, of classical and thing. So classical gives the best observables, right? Maximum observables, but quantum gives very minimal observables, close to zero. That's why you cannot yet prove completely the string theory. All the people are trying to come up with some things that shows that string theory, is observable in some ways. So you need an ensemble. Uh, you have to derive from the quantum mechanics, and this ensemble is this complex thing, right? That I am talking about. So that's why it is so difficult, because the they appear as tensor or wave functions, but now they have to scalarize them to be observable. Okay, that's the key point here. So I think the observable ensembles eventually have to be scalar, and the scalarizing takes time. So that's the essence of the whole thing. So until then, the static will hold the balance and keep it there, but then a dynamicity comes when the uh, wave function is scalarized. The tensor wave function is scalarized. That's the essence of this whole thing. All right. So essentially, you can describe the a lot of this cosmic wave background and micro backhaul things. And I believe that I was talking with Laszlo last week, and if you see that video, uh, there is a chance that our Earth was a kind of a purged out starlet, and then it became either black or red giant or something that we had to figure out, small mass, and then from there the fission process started. So initially it was fusion operated starlet, but then the fuel ran out and became uh, essentially like a tiny you know red giant or something, or microbe. Then you can see that everything at the even in the smallest part of the red giant, it will be a micro black hole. But then how that dynamics works out is the whole thing. Um, so essentially that essentially produces fission process and then Pangea and things like that, as we know. And this fission process eventually breaks apart with probably there might have asteroid or meteoroid collision, which produces the fission, give the enough power, enough energy to the surface, and then the whole thing started, and then you have the comets and things, then it produces the marsh gas. So this interaction is quite likely because we see that this is not happening in all the planets for sure. It's not. So Earth has some unique features, and this unique features is because of particular way it's oriented, particular way the collisions happen. So happened that Goldilocks zone came to Earth. You know, so the specific things are important because if all the planets are of the same kind interior, then why didn't same thing happen in other planets? We don't see that, right? Nearby planets, at least, we are not seeing the life like rich life that Earth has. They may have some still microbial organism could be there, but not anything like on Earth, right? So that why is that difference? And this is because of this reason. Specific events come together. Uh, the meteoroid, everything coming together one place is started the fission process, and this fission process then create the magma and the mantle, and from there you have the volcanoes coming. So all these micro events are so important to creation of life. And then you have the rich rock like calcium and silicide. Then you have the calcium carbonate forming limestone, like I mentioned, and the calcium becomes the part of the life aspects, all the bones and everything, and even for plants, the calcium is so important. That's important backbone of the whole thing. Then you have from there the carbon dioxide cycle produces the other process which produces water and things like that. And then you have the aeration process, the oxygen carbon dioxide circle produces the plant life, and the marsh gas now, which is hydrocarbon, changed uh, changed again. They dissipate into carbon dioxide, hydrocarbons, uh, and then higher forms. They build up amoeba, which has you know uh, which has the genetics, because now with this fission process you can produce nitrogen, and then nitrogen you have ammonia, and then it produces the cellular the genes which depends on this uh, particular ammonium phosphate and things like that coming. So the life needs much more complex uh, elements coming together, the iron, things like that coming. So all these are very important part, and then your interaction that I talked about in the last week. So the life process can be briefly described in terms of this evolution of the fission process. The fusion becomes the fission process, um, and then you have the interaction with meteorites and astro objects. So this is an important part. And so, but fundamentally, they all break down to 0 point and micro backward. That's the idea. That's a fundamental element. That's what this theory points out. Then we can see quantum gravity and brain theory. We have to describe how things are at the quantum level. So in brain, so we know the strings, they have to form like a brain, and then they vibrate, the brain vibrate. That's how they start having the gravitational effect. So microgravitational effects then come into picture there. How the superluminous condensates become uh, become matter. That's where we are trying to how the particles. That's the essence of the whole aspect. So how the asymmetry come to picture, things like that. matter, antimatter. So the dark matter itself uh, very well could be the monopole. The monopole is the key thing that gives the supplies, but the monopoles are disarranged, so they appear as dark. So two aspects are there. One of them is the monopoles. Unless they are dipoles, they don't have the horde, which is important to produce the electromagnetic effect, which is the light. So, so they appear, are just monopoles. They will appear as dark. Secondly, they can travel faster than speed of light. So they have superluminary things. So anything that is faster than speed of light again can appear as dark. So you have two things compounded to become dark, because the dark matter is of dark energy much more than being just dark, because we see dark, but they're still mesoscopic. They are still there because they're in the infrared. You can see and things like that. So they are not dark matter in that sense. They are still visible, but visible in a different sense. Visible, not just the visible spectrum, the white, the color spectrum, but also infrared and then ultraviolet, things like that are all part of this visible universe. But dark matter is entirely different, as we know. It has special features that it has, gravitational effect, but it does not have other effects. So that specific aspects you have to explain, and this is the double aspect of the fact that the monopoles exist, and also is faster than speed of light. These two together act as having. So the monopoles give the energy, very high energies, much higher energies than anything else. One monopole has much more energy than all of Earth. Um, so so that energy is what translates to the dark energy, things like that eventually dark matter actually. Then faster than speed of light, then will appear as. So they will all appear as that. It's an illusionary effect, the dark matter, dark energy, because we are accounting for the whole matter of the universe, and then that we need the dark matter to explain that, right? The curves, the astronomical, the astrophysical aspects. Uh, so essentially, when we form this theory, we can explain the dark matter, dark energy, because the enormity of the energy we have to explain. This is the whole. In conclusion, then, hot PDP mechanism, everything can be, we have come up with uh, the whole idea from abstract level, very abstract level. And the recent papers I have shown that that it all starts from a highly abstract physics, and then you come up with experimental physics from there. Um, so the question is there a universal algorithm that if you can come up with that, when you simulate in a computer, we should be able to see exactly how genesis occurred, how all the way to present, the beginning to the end, to the present side. But there may not be a big bang or a particular beginning of the universe. That's what it proves. The supernova thing is just matter of the process coming together with the hot PDP mechanism, create the particles, the phases. So the phases still exist. Superluminous phase. Then you have the vacuum phase. Only we cannot really, observe them in our normal life. Then you have subluminal. We are the subluminal phase. We can actually experience that. Uh, that's the question I'm talking about. Will monopole solve the problem having dark matter, dark energy, along with the fact that it's superluminal? I should add that aspect. So that's the granulified theory says that there has to be monopoles to account for all these energies, because it can account for the energies. So the understanding for this, understanding of superluminal condensates, latent counter gravity, deeper understanding. So you need to uh, get understanding of the superluminal aspects, the faster than speed of light. So again, Emmanuel is going to touch upon more about that, more specific experimental methods to measure that. Okay, these are some of the, you know, uh, it's not all inclusive, just a chosen a few references, chosen references, just at random. There are a lot more references. I have more than 40, more than 50 peer-reviewed publications with various teams on astrophysics, on discontinuum physics with Amory Taylor, astrophysics with Manuel Maraver. Then I have papers together with Christopher and Emmanuel was the very first one, Emmanuel Macrolacus, superlunar aspects. Uh, we started doing that, and I did the math, that Helmholtz decomposition matrix. Then with then when Song was there, so we all put together John Hall about the Horde mechanism, and we are publishing different journals as well, and that's represented here. So there's a whole lot of experiments that was going on. And then I am not going to probably not touch upon this, but mainly what the logic behind, how the logic was defined. I don't want to go into detail about that. Later on, somebody's interested, I can go into detail. But it starts from theoretical. I just want to point out. And then from theory, you come up with the physics. So physics is very important, the observation of physics. So that has been sidelined now. And that's the bigger, we want to bring it back to the front and center of the whole thing. The physics, the observation from the basics of that. So this and the real aspects, that mesoscopic observations, it's important. And finally, we have to explain that the observers themselves, the ensembles like they talked about from the quantum mechanics, how you come up with that scalarizing aspect, things like that. Uh, Bohr's rule, you have the Bohr's rule, uh, things like that. Then the experimental things, because you have to prove with experiments. So how do you come up with the proper experimental designs? So these are some of the techniques, uh, like hadron collider, things like that. Hopefully, when I go there, some of it you can talk about measurements. Again, there's a big measurement problem, right? How do you resolve that? We can measure with our mind, surprisingly, and that's another aspect. The quorum. How do you bring about the quorum for people to come together and not just debate but discuss and also come up with some agreement, right? So we have to put our puzzles together and see how they come together, questions and answers, and that we I will encourage people to ask important questions on this one. Literature available. There's so much literature, right? And then this interesting aspect of, I'm going to talk about the documentary movie. Just want to point out, it's in the making. Just started to make that. And here is mainly periodic local system, how the global system, how it became very local. And we are on the time loop aspects, things like that. Then the ball lightning that uh, eventually, I think Laszlo is the main person who's doing that. Then the traffic map of the physics. That's a very interesting thing. That's ongoing things, and how the categories come together to form, functionals and then functions, things like that. Uh, so the monopoles, for example, are just obtained as categories in the superlunar thing. But then they start interacting and produce functionals, the groups, they come together. And then the functions, which creates the flow, which creates the real matter, which real particle universe. So this is the essence of the whole thing. So essentially, that will conclude my presentation for this uh, aspect. So I think I just want to bring out the important points that I want to talk about in this one, and then hopefully next week and following week, everybody else also who are want to practice uh, for this and give a brief thing so the others can look at it and see some improvement. I appreciate people giving me feedback and editing. Christopher already has given that, so I made some changes. But some of the things how I could simplify because yeah, it is taking about 35 minutes or so. May talk. Uh, I have 45 minutes, so it's very close to the time that's using. I can reduce some of it, but seems like if I go into details, then I about the highlights, then it may take a little bit time. So I can reduce it or edit it according to how people will perceive it. And I appreciate the feedback. And also, uh, we can all practice and then ensure that we are ready and we feel more confident of presenting there. And I think that's a good idea for us to do that in the subsequent weeks. We'll have enough time. I think with that, I like to close this one. And happy Easter to all of you. Uh, Easter Sunday, the vacation, and then hope to see you all, you know, next week so that we can resume our final preparations for the conference that's coming up in a month's time. So almost we are closing in on the on that on our